and welcome to day 2 of our rational exponents and radicals. And we are going to start this off first by going to the last page of your notes. And what you are going to do is fill in these power tables. So I'm going to leave that here, and you can go ahead and pause the video to copy these down. But essentially what these is these are your powers of 2. So obviously 2 to the first power is 2. 2 squared is 4. 2 to the third power is 8, and so on all the way to the 10th power. And you'll notice that I don't have them completely filled out for all of the numbers, and that's because we're really not going to work with numbers that are larger than this, and some of them we're not even going to work with. Like, you might never see that number that big. So you could fill these all the way up to the 10th power for each number, or you can just use the ones I have here. So go ahead and pause the video to get those copied down, and you're going to be referring to these tables throughout the notes and your homework tonight. So once you have those down, we are going to jump into rational exponents. So what we do with rational exponents here is we are going to be converting back and forth from exponent form to radical form, and we use that when we have fractional exponents. So when we have a exponent that's a fraction, that denominator indicates what the radical is. So that indicates our index. And then obviously a is our radicand, what's inside the radical. So a to the 1 over n power would be the nth root of a. Okay. If you have a numerator and a denominator in your exponent, again, that's like if you raised it to another power, you multiply that. So m over n exponent, n is still your index, so that's what's going to your radical, and you're actually going to also be raising it to that m power. Okay. So again, a to the m over n power, n indicates what your radical is, and you're still raising it to the m power. And we can go back and forth. If you're starting out here, you can go back and forth from radical form to exponent form. Okay, so first off, what we're going to do on the first couple, and again, we're starting at 24 because we left off at 23 on day 1 notes, so we're just picking up where we left off. We are going to rewrite these using rational exponents, so our fraction exponents. So again, 15 is my radicand, that's going to be a, so 15. And I don't have any kind of exponent on the 15 or like around parentheses, so my numerator is going to be 1. And I get my denominator from my index. So what this radical is, and this is the 7th root, so this is going to be 15 to the 1/7 power. Okay. Now let's look at 25. My radicand is 18. And this time, it's being raised to the 4th power, so that's going to be my numerator. And my index is 3. This is the cube root. So 18 to the 4/3 power. 26. My radicand is x. It's being raised to the 5th power. So that's going to be my numerator. And then this is square root. Remember, when there's no number there, we assume that it's a square root. So that is going to be over 2. So x to the 5/2 power. Okay. So that is going from radical to rational exponent form. Now on 27 and 28, we're going the other way around. We're going from rational exponent form into radical form. So the thing that's being raised to the exponent, that's what's going to be inside of your radical. My numerator indicates the power on my radicand, and the denominator indicates the index. So here's one way to write that, or you could also write it this way. Okay, so just as we saw above, this also comes from a to the m over n power, or this comes from the a to the m over n power. Okay, so both of these are acceptable ways to write that in radical form. Okay, now with 28, we have a negative exponent. So before we write this in radical form, we need to make that have a positive exponent. So remember, for negative exponents, to make them positive, we move their location. So we're going to move this into the denominator. So now it's 1 over x to the 3/2 power. And now we're ready to write that as a radical. So again, this is going to stay in the denominator. X is what's going inside of my radical. My numerator in my exponent is 3, so that means x to the 3rd. And then my denominator is 2, so that's square root. So we can just leave that as the radical. We don't need to write 2 because we assume that it's 2. Or you could also write it this way. Square root of x cubed. Both of those are acceptable. Okay. Now, the rest of these where we're evaluating without a calculator, this is where you're going to be using those power tables that we filled out at the very beginning. So, some of these should be very easy to you right off the bat, like 29, square root of 16, that is 4, right? You know that, we have it memorized, no big deal. But now looking at 29, we have the cubed root of 27 squared. And I know you're probably already thinking, how the heck am I going to do that without a calculator? I'm taking the cube root of something. Now, wouldn't it be a lot easier to take the cube root of a perfect cube? 27 itself might be a perfect cube. Let's look. If I look, where do I have the number 27? In my 3 power table. 3 to the 2 to the 3rd power. 27 is actually 3 to the 3rd power. So I'm going to rewrite this radical as the cubed root of 3 cubed squared. Okay? Now, what is the cubed root of 3 squared, right? It's like when you take the square root of a square, they cancel out. So this is now just 3 squared, which is 9. Okay? Now let's take another look at 30. The cube root of 125. Is 125 a perfect cube? Let's look. If we go to our power table of 5, 5 squared, 5 to the 3rd is 125. So 125 actually is a perfect cube. So that is going to be 5. Let's take a look at 31. The 4th root of 256 cubed. So once again, my hope is to find a perfect 4th or possibly even a perfect square. So 256. Let's look on our list for the number 256. If I look on my power of 4, 4 to the 2, 3, 4th power is 256. So 256 is a perfect 4th. So I'm going to, again, rewrite this as the 4th root of 4 to the 4th power cubed. So again, the 4th root of 4 to the 4th, that's just going to cancel with the exponent. So that's going to be 4 cubed, which is, if you don't have it memorized, you can look back at your power table, but that is going to be 64. Okay. All right, so hopefully you're finding a rhythm by now. 27 to the 4/3 power. So first let's rewrite this in radical form. So 27 is what's going to be inside of our radical. The denominator indicates my index, so the cubed root of 27 to the 4th power. Okay. So cube root of 27, we already know that 27 is a perfect cube. It is 3 cubed, so that is going to be the cubed root of 3 cubed to the 4th power. That cube root of 3 cubed cancels, so that's 3 to the 4th power, which again, we can look at our power table to find that it is 81. All right, 33. Once again, we need to write this in radical form, but I've got a negative exponent, so let's make that positive before we do anything else. So that is going to be 1 over 32 to the 2/5 power. Then rewriting that as a radical, that is going to be the 5th root of 32 squared. So the 5th root of 32. Let's see if 32 is a perfect 5th. And looking at my table, 2 to the 2, 3, 4, 5 power is 32. So 32 is a perfect 5th. So again, I'm going to rewrite this as 1 over the 5th root of 2 to the 5th power squared. So that's going to be 1 over 2 squared, which is 1 over 4. All right, 34, square root of negative 100. We cannot take even roots of negative numbers, so this one has no solution or is not possible. 35, square root of 4 over 9, and we're just tacking on a negative at the very end. So this is just going to be negative 2/3. And now 36. The cubed root of negative 1 over 64. We can take odd roots of negative numbers, so we know that our root answer is going to be a negative value. And so now we need to take the cubed root of 1 and the cubed root of 64. Well, the cube root of 1 is just going to be 1, so that one's easy. So that's just going to be negative 1 over. Let's see if 64 is a perfect cube. And it is. 4 cubed is 64. So that is going to be negative 1 over 4. Okay? So again, you're really going to want to just keep those power charts, those power tables handy while you're doing your homework because it's going to make things significantly quicker for you. Okay? All right, now on the rest of these, we are using our properties of exponents to simplify. So t times the cubed root of t to the 6th power. Let's think about this. T to the 6th power. This t that's outside is going to stay. T to the 6th power is the same thing as t cubed times t cubed, right? Because when I'm multiplying like terms, I add their exponents. 3 plus 3 is 6. Now the cubed root of t cubed would be t, and the cubed root of t cubed would be t. So I have that t on the outside. The cubed root of t cubed is t. The cubed root of t cubed is t. So what I was able to pull out from the cubed root here was t squared. So my final answer is going to be t cubed, but a shortcut to these types of problems instead of having to rewrite it this way would be if the exponent inside of your radical is divisible by your index, like 6 is divisible by 3, the root of that value is going to be that exponent divided by your index. So you could have saved yourself this trouble and just gone, okay, 6 is divisible by 3, 6 divided by 3 is 2, so that's going to leave me with t squared. Okay, so we will practice that some more on these next couple problems, but let's look at 38 now. Properties of exponents. What I need to do is rewrite these both in exponential form. So this is going to be x to the 1/2 over x to the 3 over 2, or 3/2. So I'm dividing like terms. What do I do with their exponents? I subtract them, and it's going to go where the larger exponent is. So 3/2 is bigger than 1/2, so I'm going to subtract that, and that's going to leave me with 1 over x to the 2 over 2, or which is just x to the 1st power. 39, z squared is on the outside, and I'm looking for the square root of y to the 5th times z to the 4th. Now, part of this is pretty easy because we're taking the square root, so our index is 2. 5 is not evenly divisible by 2, but 4 is. So we know that we are going to get 4 divided by 2 is 2, so we know that that's going to be that z squared on the outside, and this is going to give us also z squared. So that leaves us with y to the 5th on the inside. Now, what do we do with that y to the 5th? I know for sure I can take out some y's. So what we need to look for is the largest multiple of 2 that's part of 5, and that's going to be y to the 4th. So I can rewrite this. Z squared times z squared is z to the 4th. So this is going to be the square root of y to the 4th times y, right? My exponents would still add up to 5. So now this y to the 4th is going to come out looking like y squared because, again, 4 divided by 2 is 2. So z to the 4th, y squared, and what's left inside our radical is that y. So here's the final answer for 39. Let's look at 40. Wow, I've got a lot of x's here. I need to rewrite everything in exponent form. So that x on the top stays the same. That is x to the 1/2. And then in the bottom, again, I have x to the 3/2. So let's combine our like terms in the top. This is x to the 1 plus x to the 1/2. So that's x to the 3/2 over x to the 3/2. Well, those are the same, so those divide evenly by each other, and that gives us 1 as the resulting answer. Okay. 41. Again, I need to rewrite these in exponent form. So I am going to distribute, I've got a power raised to a power, that's x to the 6/4 times x to the negative 1/2. 6/4 actually does reduce, that's a fraction, so you can write it in simplest form. That's going to be x to the 3/2, x to the negative 1/2. Multiplying like terms, I'm going to add their exponents. 3 over 2 minus 1/2 is going to be x to the 2 over 2, which is just x to the 1st power, or x. All right. Problem on this side, again, I need to distribute these. So I've got a fraction times a fraction, so that's top times top, and bottom times bottom. So 6 over 15, that does simplify. The common factor between 6 and 15 is 3, so that is going to be x to the 2/5 as the final answer.